Welcome back to the Idealcast. I'm your host, Gene Kim. Today we have on Scott Havens, currently Director, Head of Wayfair Fulfillment Network Engineering. This episode is made possible with the support from ServiceNow. Take the risk out of going fast. If you need to eliminate friction between dev and ops, head to servicenow.com/devops to find out more. You're listening to the Idealcast with Gene Kim, brought to you by IT Revolution. I am so excited that my guest is Scott Havens, who is currently Director, Head of Wayfair Fulfillment Network Engineering. So in the previous episode, you got to hear him give one of my favorite presentations of all time. It's a presentation he did at the 2019 DevOps Enterprise Summit in Las Vegas, where he talked about how e-commerce systems work and what he did to massively simplify the systems that powered Wal-Mart, while also making them more testable, reliable, cheaper to operate, and easier to change. He described the work that he did as Director of Software Engineering at Jet.com and later Walmart Labs. His remit was to rebuild the entire inventory management systems for Walmart, the world's largest company. He earned this right by the amazing work he did rebuilding the incredible systems that powered Jet.com. It powered the inventory management systems, order management, transportation, available to promise, available to ship, and tons of other critical processes that almost go right at an online retailer. In this episode, we will learn more about his views on what makes great architectures great, the gruesome details on what happens when an API call requires 23 other deeply nested synchronous remote procedure calls to return a correct answer, how one actually implements event sourcing patterns on Walmart's scale, and the functional programming principles that it depends upon, the challenges of managing inventory at Walmart, which is a vast supply chain in its own rights, and just how much category theory do you actually need to know to do functional programming. This was such a fun interview for me because as much as I learned from his DevOps Enterprise talk, I learned a ton more from his amazing explanations. Okay, Scott, I've described you in my words. Can you describe yourself in your own words and describe what you've been working on these days?
My name is Scott Havens. Thank you very much for that introduction. I'm a huge fan of functional programming principles and how you can use them to build enormous systems operating at scales that bypass anything that you might actually need to see in the real world. This often means a switch to asynchronous thinking, which is big change for a lot of people from the synchronous mindset. And it's a switch from an object-oriented mindset to an immutability-first mindset, a purity-first mindset, and being able to think about the duality of code and data in your systems. These have huge practical benefits. They're not just theoretical. As you're building these systems, you actually see the practical advantages in terms of latency, in terms of observability in systems, and being able to prove that your systems are doing what you want them to do.
It almost seems that you're almost minimizing kind of your achievements just by pigeonholing it into just functional programming. You have a very drastically different view of the world in terms of the architecture should reside in, as well as evident through your talk that you did about your work at Walmart and later modus operandi. Can you extend what you just said and incorporate kind of how you view architecture fitting in as well?
The point of any architecture is to build a collection of systems that you understand well and that solve the business domain problem at hand. I like to think about what the end goal you're actually trying to solve. Think about, if you're in retail, what is the customer actually trying to accomplish? Work on making it as easy as possible for the customer to accomplish that and pull out of the hot path all of the work that needs to be done to get there in the first place. That means make all of as much processing as possible asynchronous, done in an event-driven manner where you can map out all of the domain events over a period of time without making the customer wait for you to solve all these problems in real time.
Wow. So let's to make this concrete and maybe to make sure that everyone fully appreciates the awe in which I view your work. I recently rewatched your DevOps Enterprise Summit talk from Vegas 2019. And has mentioned to you before, it is just as breathtaking now as it was listening to it a year ago. And if I took notes correctly, there was one particular example that I found utterly riveting. You specifically talked about a specific capability that most e-commerce sites need to do, which is for a given product, is the item available for me to order it? And you described that how in the Walmart context, to render that information required 23 separate service API calls. And each one of these 23 service API calls, it would have to respond in 50 milliseconds. They would have to have 5 nines of availability in order for the customer to get a response within a third of a second. And that any one of these services going down would potentially take down the ability to tell the customer anything at all. Can you tell me about why that's so bad and maybe how it offends you both in the realm of functional programming principles as well as the architectural principles that you hold so dear?
Sure. Customer-facing systems need to have an enormous uptime, especially in a retail environment. The next retailer is just a click away. So if you need to have your systems up and running all the time with minimum latency. Every click the customer does needs to return results as quickly as possible without any failures. That means in the real world, you're talking 4 nines of uptime, more or less, with really low latencies. Has to, anything over 300 milliseconds, the longer customer has to wait, the more likely they are just to give up and switch to a competitor. It's really expensive to have systems running at that with that kind of uptime and that kind of latency. You need to have staff on hand all the time, dealing with all of these redundant systems, making sure that they don't break, or if they do, they get fixed as quickly as possible, 24 hours around the clock. When these systems then have to call other systems, and those systems then call other systems and call other systems all in real time, that means that every single one of these supporting systems, every one of these supporting services needs to have even better uptime. Because the effects of downtime are multiplicative. If any one of those systems is down, then the whole system is down. And that ends up being really expensive. If you have call after call after call, every single one of these is running at 5 nines uptime. It's incredibly expensive. If you can get all of those systems out of the hot path, then you don't have to be supporting all of these additional systems at such an expensive level. It's okay if it's okay that they go down every once in a while. You don't have to staff them 24/7. You don't have to design them in a way that they can survive a nuclear blast and on one side of the country, and they're still operating out of the other. The key to doing that is switching these from synchronous service calls that are RPC type requests to event-driven systems, where as they're processing their own changes, they will push via messages any of the relevant changes to the customer-facing system. If some of those updates happen, a few seconds late or a few minutes late, it doesn't matter because the customer-facing site will still continue running that whole time. So you're taking all of the complicated computations out of the hot path and letting them run at a much lower service level for much cheaper.
And so if I'm a customer going to a product page, I'll see all the product details, I'll see the add shopping cart button, but then I'll also see, X number in stock. So when you talk about item availability, it's that, right? In other words, it's available in stock, and not only is it available in stock, but it's available to ship to me. Can you give us a sense of what are those 23 API calls required to render that simple piece of information?
Yeah, the obvious ones are that you need to know that an item is in stock in a warehouse, and you need to know how many reservations from other orders are against that already. But then you need to know, is that warehouse open? Is that warehouse eligible to ship to your particular location? Maybe it's located in a different country. Maybe that warehouse is going to be down for some kind of physical maintenance. Maybe the item isn't eligible to be sold on a certain site because of some kind of agreement with the manufacturer.
Yeah, but I'm getting stressed out just even thinking about it. I've never worked in a retail system, so the one that I found particularly stressful sounding is the reservation one. If I place an order in my shopping cart and I might not ever hit ship, and so that reservation is no longer valid. Is my understanding correct?
There are different kinds of reservations you can do in the retail world. We've looked at whether you want to reserve as soon as you are purchasing the item, or if you want to reserve earlier, maybe on add to cart. It turns out that in the real world, we don't actually want to reserve on add to cart very often because it will just get stuck in a cart. People won't necessarily buy it. And we don't care if that customer buys it versus a different customer buying it. It's going to be the same money for us one way or the other. Mm-hmm. What we do care about is the customer experience and making sure the customer is never told that, yes, you definitely are going to be able to buy this. And after they've paid for it, they get told later, oh, turns out we actually sold it to someone else. Or, oh no, turns out that for whatever reason, we thought we had it to give to you, and we don't actually. So
the reservation is that period of time between I submit the order and is on the way to me. Is that right?
Exactly. Exactly.
So the windows are even smaller.
It becomes a daunting technical problem when you look at days like Black Friday, where you might have a special where a Nintendo Switch, you have perhaps 100,000 of them in stock, and you'll have 500,000 people all hitting the site at the exact same time at midnight when that deal comes on, all trying to add to cart and check out at the exact same time within a minute. So you have to guarantee that those first 100,000 customers will get that item and be told that they get it, but the 100,000th and first customer is told, no, sorry, you can't do that.
Interesting. Sorry. It strikes me that this is a particularly hard part of the ordering domain.
It is. This is one of the only areas of anything in e-commerce that needs to be strictly serialized. It means that every single customer could be interfering with every other single customer simultaneously. So every single request needs to have a strict order behind it. You need to know that this request came before this one and comes after the previous one. And that ties in really closely with event-sourced systems, where you want to have all of the events in a strict order, where you know that this is the 1,000th event, this is the 1,000th first, etc.
Awesome. So can we explore what it might feel like to be part of one of those 23 teams? Some of the things I heard was you have to over-provision capacity, you have to be on call 24 hours a day just because you are in the hot path. It specifically said it's difficult to test things, but I have to imagine it's also difficult to implement things because of the interdependent nature of the systems. Can you talk about that?
When you have one of these systems that's providing one dimension of availability, whether it's what your system is responsible for saying whether the warehouse is open on certain days, or your system is deciding what kind of carriers and carrier methods are possible for transporting the goods. If you're building a system that is designed to be called synchronously from some availability API, it means that your own system has to be up all of the time, running in production with no downtime, no errors. And it makes that very hard to both build new features behind an existing API and to roll out new features and to test these new features in production. One of the things that has become very clear to me dealing with these massive distributed systems is that you can never fully test something before it gets into production. The scale is just not going to be there in whatever kind of staging environment. The right kinds of inputs are never going to be there in your staging and testing environment. When you have a synchronous system that has to respond to all of these requests in real time, adding a new feature and deploying a new feature there's a lot of overhead to it. You need to deploy in parallel. You need to do a little bit of canary where maybe 5% of traffic gets rolled over. You need to be very much on the lookout for any errors and be ready to roll back the instant there are any errors. The roll-up process ends up having just a lot of overhead, and or to get rid of that overhead takes a lot of automation upfront to get that deploy process.
So just if I understand you correctly, so this is now speaking to just because you're handling live traffic all the time, there's just a lot of infrastructure required to make sure that you can do controlled deployments so that if there is something bad happening, you don't take out 100% of your traffic or introduce errors into all of the incoming requests.
Exactly. Safety is very difficult to guarantee when you're dealing with live synchronous systems.
Right.
You have very strict performance requirements as well, performance and scalability requirements that have to be met up front. For every feature that you are writing, you have to make sure that adding on that feature doesn't bump your service level outside of your SLA. If it adds 50 milliseconds on, the feature may work, but you're now out of your SLA, and it's hard to test that in advance as well.
And so can you talk about maybe the correctness aspects? I mean, is it more difficult to actually establish the correctness of any new code?
It's not necessarily difficult within a given system to test the correctness. However, with a live system, you don't know what the dependent system is going to do with your response. For better or for worse, contracts between systems nowadays are usually very loose. There's some kind of JSON-based RPC, or even if it's something that's a little bit more strongly typed, like protobuf, you're still going to have some categories of errors that aren't being caught by your type system. So you never know what your downstream system is going to do with your new feature. So correctness within your own domain, great, but correctness further down, you can't really predict that. And you may blow up a live system because of that.
And so if we don't want to do that, then now we have to start coordinating with other teams and the dependent systems to make sure that any changes I make don't accidentally blow up a nearby system or a distant part of the system.
Yeah, that ends up being a massive level of coordination, because you aren't just coordinating with your single downstream system or upstream, depending on your perspective. It ends up being the entire chain of synchronous calls all the way up to the customer-facing API that all have to be tested in concert to make sure that the customer is still seeing the right thing when you roll out your change 5 calls down.
And so I'm kind of assuming that this means in order to do this, now you have to test it in the presence of all the other systems. I'm assuming it'd be some sort of huge integrated test environment where all the components have stood up so that you can somehow test the system as a whole.
That is one way to approach it, but in a distributed system, like I said earlier, alluded to, you're still not going to get the right kind of scale, the right distribution of inputs. It ends up being a testing in production that is coordinated across all of these teams, and just crossing fingers, hoping that ends up working right.
I have to imagine if I'm going to roll out something new in production, there's going to be a lot of coordination to make sure that everyone else knows that we're doing it at a safe time. Is that right?
You end up seeing that. You have your schedules where team A is allowed to test on this day. You have a 2-hour window that everyone else has to be aware of and work around. And team B is allowed to test in the next 2-hour window. And it really slows down your release cadence because of the amount of coordination overhead across all of these teams. You're not able to act as independent teams like you'd want. It is all really one big team that has these coordination problems.
Our sponsor today is ServiceNow, and I'm grateful that they have also been a longtime supporter of the DevOps Enterprise Summit, the conference for technology leaders of large, complex organizations. Join us there and visit the ServiceNow booth to see all the ways they are supporting the DevOps Enterprise community. ServiceNow connects the work going on in DevOps pipelines to the operational work already being managed in ServiceNow to create a seamless governance layer for delivering apps using DevOps at high velocity. For organizations that need the assurance of change control but want to avoid slowing down developers, ServiceNow can completely automate the gathering of information from the pipeline, the creation of change requests, and the approval of those changes. This eliminates admin work and keeps developers in the tools they know and love while improving the quality and simplifying any future audit activities. ServiceNow also uses this connection to add value stream management to DevOps, joining teams and information from ideas to value realization so that they can gain insights into what's happening and understand how value is being delivered. In fact, ServiceNow was named a leader in the Forrester Wave for value stream management solutions. If you need to eliminate friction between dev and ops, head to servicenow.com/DevOps to find out more. So what were the effects of all this inadvertent coupling? Was there finger pointing and blame? Was it fear? Was it inability to make changes as quickly as you want? I mean, if you were to sort of project out kind of like what were the behaviors in the absence of this that you would point to as very unhelpful?
One of the results was that the time from writing a feature to the time that it was not just deployed in production, but active and affecting the customer experience was far higher than it needed to be. That we had to wait for every single team to be able to test a given feature simultaneously. If you're doing that in order, you're having to coordinate all of these teams on every release to do all of the testing through the entire service call graph before you're able to move on to releasing the next feature, even if the code had been done for that weeks or months ago. So that was one effect. Two, is kind of the corollary to that, and that because people didn't want to wait as long, they would shove more and more features into each release that became much larger releases instead of every few hours or however often they wanted to. It became weekly releases or semi-weekly releases. And that introduced more risk into the system, that every change was that much more difficult to test and much more risky and likely to cause a problem and require rollbacks. All of this added together to mean that we ended up having to do windows where once every few weeks to every couple months, depending on the set of systems, in the middle of the night, you would do your deploy, hope that nothing broke, run through all of your tests, and if everything's okay, then you make that deploy active. Otherwise, you have to roll everything back and maybe try again next week. It's the exact opposite of why you want it, or one of the reasons you wanted to have services in the first place is to decouple all of that testing, all of that deployment. It really only got you part of the way in that you're able to develop the features independently, but having code sitting in main doesn't help the customer. It only helps the customer once it's actually in production and working. It meant that when anything went wrong in production, there would be a single call that multiple representatives of every single team would be on. No one really knows what the problem is. And you have, it's really difficult to get anything done when you have 100 people on the same call trying to solve what the problem might be.
That's evident. No,
yes.
Of the worst sort. Okay. Brilliant. Despite all of the decomposition that was done. Okay. Awesome. So, I listened to your talk twice before it really sunk in what you did. I certainly understood I think on the first listening to it, when I watched your presentation at Microsoft Build, I definitely did, I think, understand that you were able to, in a breathtaking way, reduce the number of calls from 23 service API calls down to 2. But what I didn't fully appreciate was that you were actually then pre-computing all of those results in advance so that those 2 service API calls were actually lookups, a key value lookup. So the simplest type of database access that you can come up with. Am I understanding that correctly? That this was really you're recomputing for every item, warehouse, zip code, and so forth, right? Is it available? Did I capture that correctly?
Exactly. One of the principles of functional programming that I've taken from the low-level code and applied to systems as a whole is the duality of code and data. All of these calls are some kind of computation. If you know the domain of all the possible inputs in advance, you can pre-compute for all of those dimensions, all possible outputs, and store those in your massive key value store. And because you're treating it as an actual function, the entire system, you get all of the nice benefits of what you could see in low-level functions, things like being able to query your systems. When you look at all of your different inputs, maybe some of them are fairly simple and you have a small range of output possibilities, but maybe the cardinality is just too high to be able to pre-compute everything. For example, if you're trying to compute whether you're able to ship something and how much it's going to cost, you might include, as an example, your source warehouse, maybe 12 of them, your destination zip code, 44,000, a handful of carriers, handful of carrier methods. All of these are minimal in terms of their cardinality. But then you look at your weight as an input. And if you're talking, like, say, a tenth of an ounce to 1,000 pounds, that's 160,000 different possibilities for that input. But because you've decided to treat the entire system as a function, you can use the concept of currying. Currying being that you can take a function of multiple inputs and break it down into multiple functions of just one input or a handful of inputs. So this whole system, you could say, I want to pre-compute all of the inputs for the warehouse, the zip code, the carrier methods, and that'll give you maybe 10 million, which is pretty reasonable for your key value store, and a separate function or a separate system that then takes one of those key value lookups and only uses that and the weight to produce your final value. In functional programming, if your functions are actually pure, it means that for any arbitrary set of input parameters for your function, you can split your function up using any combination of those input parameters and then compose the resulting functions to get the exact same result as you would have before.
Gene here. I want to mention just how incredible it is for me to be able to finally more fully understand how e-commerce actually works, whether it is the front-end ordering processes, the back-end inventory management and reservation processes. These are things I've never fully understood, even though I am a pretty heavy consumer of e-commerce properties, and even more so since the global pandemic has reduced the ability for physical commerce. I think this is such a great talk to follow Dr. Stephen Spear on the physical supply chains, as well as Dr. Gail Murphy on software architecture and software supply chains. By the way, what I do know, I am so grateful to both Ron Forrester and Courtney Kistler back when they were both at Nike, who let me visit them during their Air Jordan 11 shoe launches. These are the high-heat e-commerce launches where they sold tens of thousands of shoes in minutes. The Black Friday launches in the Unicorn Project were very much modeled after what I got to see there. Okay, my first elaboration is about currying. I thought it was so cool that Scott brought this up because it was so surprising and illuminating. So to put this into context, currying is often talked about in functional programming alongside the notion of function composition. The name comes from Dr. Haskell Curry, of which the Haskell programming language is named after. He was an American mathematician and logician born in 1900 who got his PhD in mathematics. So let's talk about function composition first. It basically states that if you have a function f that takes an a and returns b, and a function g which takes that b and returns c, then you can substitute functions f and g with function h, which takes that a and returns c. So you might recognize this as the property of associativity. You can replace that with what is often called f.g. So here is a concrete example from the Wikipedia entry on function composition. Suppose you have a function that returns an airplane's altitude at time t. Call that function a that accepts t. And you have a second function that returns the air pressure at that given altitude. Call that function p that accepts x. Then you can return one function, p.a, that takes a time, and it will return the pressure on the plane at that time t. It's kind of hard to describe these very succinct equations in audio. So this is very close to the concept of currying. According to the Wikipedia page for currying, suppose you have a function that takes three arguments, a, b, and c, that returns x. You can curry that function into three unary functions, x, y, and z, which can all be composed together to return that same value as that function f. So to make this very concrete, you've heard Scott talk about how it required initially 23 deeply nested API calls to determine item availability. He's saying that there's a way that you can treat most of these API calls as a pure function, which allows you to curry them, which allows him to pre-compute the values of the entire function. So to talk about how he exactly did that, let's go to number 2, which is a concept of cardinality. So if I understand correctly, we can loosely interpret the term cardinality as the number of elements in a domain, or the size of that set. So Scott is saying that the item availability function takes the input product, SKUs, warehouse, carrier, zip code, and weight. and it returns how much does it cost to ship it and how long will it take to get there. So the cardinality of the inputs are as follows. The number of product SKUs is, say, 75 million. The cardinality of warehouses is about 12. The cardinality of zip codes is about 43,000. The number of carriers is about a dozen. And the cardinality of weight is about 160,000. So imagine creating a curried version of the function for each argument except for weight and the product SKUs. Those are the inputs where the cardinality is too high because it would cause the number of entries in that lookup table to be too large. The size of the lookup table, if you included product SKUs and weight, would be 7.4 times 10 to the 19th power. If you omit weight but left in product SKUs, you would get 464 trillion. And if you omit both the product SKU and the weight, you have what seems to be a very manageable 6 million entries. I think this is so amazing. Scott has described how you can go from 23 synchronous API calls, where all the computation is being done inline, to 2 function calls, where almost all of the computation has already been performed, and you merely need to look up the value in a table with about 6 million entries in it. This is such an amazing and practical way to solve a real business problem using both function composition and currying. Super cool. Number 3, Scott talks about the coupling that occurs when teams are not truly able to test independently. Even though the services behind each API may be decoupled from each other from a code architecture perspective. I think a wonderful definition of a loosely coupled architecture are when teams are able to independently develop, test, and deploy value to their customers. Scott is describing the conditions when you are able to develop independently, however, are not able to test or deploy independently. And he describes the horrible things that happen as a result. You have larger batch sizes where you are able to deploy only on fixed cadences. And because the deployments may not work every time, you then end up with more to deploy the next time around. Scott described brilliantly what happens when you have a high coordination cost. That means everyone has to be on the lookout for problems, and only a certain number, or maybe only even one team can deploy in a given period. I love that if you miss that window, you have to jam more features into the test, which reduces the likelihood of everything working, leading to even worse outcomes. And because those outcomes are so problematic, you now have to do deployments in the middle of the night. Okay, back to the interview. So let's talk about those 23 service teams. How did their world change because of this new architecture?
By switching from the synchronous calls to totally asynchronous, they were able to focus more on making sure that they were just doing the right kind of computations with scalability that they could handle on their own without being beholden to a customer-facing API, and roll out changes as they're ready to go out without coordinating testing with everyone else. Instead of having a huge redundant cluster, it is the minimal amount of services that you need to just to process what's happening on a regular basis. If it starts to fall behind, you can scale up at that point, but there's always some kind of buffer in place from the messages that they're reading from Kafka or whatever their other message queue is. And it allows for a lot more flexibility in their performance. If you make a mistake deploying, if it breaks something, that's okay. You roll it back and try again or identify what the problem was. If something rolls out and it breaks everything, again, that's okay. It's not going to cause problems until a large amount of time has passed, until things get too delayed. If you're down for 5 minutes, 10 minutes, 20 minutes, usually that's not going to be a problem. So your deploys you're able to do a lot more because you're comfortable that if there is any problem, no big deal, roll back and no one will even notice. Third, you're able to add more features, adjust your contract as you want. Because all of this is happening asynchronously, you can put your outputs into a new stream. The downstream systems that care about that data will be able to look at these new events, these new messages, whenever they get to it, when they are ready to switch over to your new output format that is providing them more data, or whatever changes that you want to make. You're not dependent on the downstream team switching over. you can just go ahead and make those changes or those new features, and they can take advantage of it when they're ready. This is an example of testing in production in a way that is safe.
Yeah.
You're always deploying your services into production, and they're running in parallel with your existing ones. Any data that you're outputting can go into a parallel stream. Again, it's happening very safely because no one's consuming it yet. And you can check your data at that point, make sure that everything that's happening it's hitting all of your SLAs, all of the data being output is correct as far as all of your testing would be concerned, but it's in the production environment. It's getting the full set of all of the possible inputs and running at the scale that is going to be necessary for it to work correctly. Just that the downstream teams will be able to switch over to the new stream at their leisure.
Incredible. Can you talk about the inputs? So I'm part of the service team. Before I had this REST API that I'm supposed to, I get a request, I put in a response. That's the inputs and the outputs. What does it look like in this new world?
The inputs are fewer than they were before. If you were managing your carrier methods, for example, you're still getting your updates on the methods from UPS, the FedEx, DHLs of the world that change your system configuration and your possible results. And you're still processing those as they happen. But the big change that for your inputs is that you no longer have your REST API or your RPC API that is exposed to the customer. That goes away. The only way that they get that data is by consuming your event stream and caching those results or doing their own computations in advance, just like you're doing. So you don't have to worry about any kind of production level RPC interface that you're supporting anymore. So with your transportation example, you still have your inputs that change what warehouses are available. Zip codes probably are not going to change. That's the configuration. Your carriers and carrier methods, you still have those as inputs. And you still have your outputs of all of the different combinations of these that you're emitting over Kafka or whatever your queuing or messaging pub subsystem is. In the service-based example, you also have to maintain REST-based or RPC API that is going to be operating at production level, production or customer-facing, exposed to the world, that may get hit by any number of requests as time goes by. In the event streaming example, you don't have to support that anymore.
And now, a message from this episode's sponsor, ServiceNow. ServiceNow connects the work going on in DevOps pipelines to the operational work already being managed in ServiceNow to create a seamless governance layer for delivering apps using DevOps at high velocity. For organizations that need the assurance of change control but want to avoid slowing down developers, ServiceNow can completely automate the gathering of information from the pipeline, the creation of change requests, and the approval of those changes. This eliminates admin work and keeps developers in the tools they know and love, while improving quality and simplifying any future audit activities. ServiceNow also uses this connection to add value stream management to DevOps, joining teams and information from ideas to value realization so that they can gain insights into what's happening and understand how value is being delivered. In fact, ServiceNow was named a leader in Forrester Wave for value stream management solutions. If you need to eliminate friction between dev and ops, head to servicenow.com/DevOps to find out more. Someone else is responsible for enumerating the universe of possibilities, and my responsibility is to generate the right computation, and then that'll go live somewhere else, eventually living in the key value store that is customer facing.
Exactly.
Okay. Awesome. What else changes for this particular team in this new world?
When the team has switched to the point that they're taking all of these messages as inputs and they are emitting these messages as outputs, suddenly the system as a whole looks very much like a function where it's not needing to do anything in the middle except its stateless computation. And that's where you get a lot of advantages in correctness, that your entire set of domain inputs, your entire range of domain outputs. You can use something like spec-based, property-based testing to make sure that all of your invariants will hold that you expect, that you'll never have a cost that goes negative for your transportation system, or your inventory counts will never go negative if it's an inventory system. You just know that that will never happen, all based in tests that are happening in code at the unit test level without ever needing to hit a database to do that.
This is kind of exposing one other thing that just shows how loosely I grasp this. So within this service, if I have an external dependency, I need information from another. How does that change for me before and after?
You may make a call up front, but ideally, that service has also switched to being an event-driven system that is pushing its own inputs into you rather than you making a call to it.
Oh my goodness. So in the ideal, it's not something I'm responsible for fetching. It is actually given to me. So it's like a pure function.
Exactly. If you're able to push this architecture all the way through, only the customer-facing API is going to be doing a live call. Everything else that contributes to that is going to do have its own inputs that are streamed to it, do whatever computation it needs, and push its outputs to the next system.
So in your presentation, you talked about just the value that was created by this. Orders of magnitude cheaper to run, easier to test, easier to implement. Looking back, are there other sort of dimensions of value that made people so happy about the work that you did?
One of the things that we get from systems like this that are event-driven is that you see so much more data that you didn't have before. Synchronous systems, all of these calls that are coming from the consumer and hitting a service, it's calling another service, calling another service. If you want to store that information for analytics purposes later, you have to go out of your way to build something that's going to capture this, that's going to siphon off all of that data and store it somewhere to get that observability. That a lot of that comes for free in these event-driven systems. You are already capturing it in virtue of needing to send it over a queue or pub sub to the downstream system. It's pretty trivial to just hook up another listener to that pub sub stream and save it off to a data lake somewhere. The data is already being put into a format that is conducive to that.
So it seems that this, as a whole, just incredibly magnificent properties. It seems to be a magnificent architectural story. And so when I think about the hallmarks of good architecture, some of the things that come to mind are the ability to be able to test your portion of the system in isolation from everyone else, the ability to do your work within your system without needing to communicate and coordinate with people outside of that service, and maybe even making large-scale changes to your part of the service without permission from anyone else. And then performing deployment, the ability to perform deployments during normal business hours with negligible downtime. So those are all markers that came from the 2017 State of DevOps report. So what are your hallmarks of great architecture?
I think all the ones you listed are fantastic. It's really important to me for architecture that people are able to pick it up quickly and understand the scope of changes that they're making, what the potential blast radius is going to be, understand hopefully that it's minimal and not be afraid of making changes. Well, in other words, there's a pit of success that as long as they understand a basic minimum about it, they can get up and running very quickly with just doing the things that they need to do to create business value while making sure that the system is going to be maintainable for the people after them. For me, a great architecture is one that allows you to make changes to your business domain, to add new features that the business domain needs, and continue to be able to keep adding those features over time in a way that doesn't slow down because of all of the debt that you have accreted over the last months, years, possibly decades, depending on your business. If your architecture allows you to make these changes in a way that the person or team making the changes can feel confident that they're not going to be breaking anything else, then that is a hallmark of great architecture, something that stands the test of time.
So you said two things, and I think it's just kind of beautifully the way you put it. If I heard you correctly, it was like, can you make the changes you need to make in the present? And will you be able to continue to be able to do that in the future? Did I oversimplify what you just said?
No, I think that's great. It's having the right levels of abstraction that you can easily identify the boundaries of what you're trying to change versus what you don't want to change. If any developer coming into that code base can say, oh, for me to make this change, here is where I need to make it, and I don't need to worry about anything else. Don't have to worry that that's going to break. Either break their code, break their deployment, break their tests, any of these pieces. I only have to look at this one area. That makes it a great architecture.
I love it. So that you're essentially encapsulating or creating these boundaries so that local failures cause only local problems, and you don't really need to have too many concerns or worry about things outside of your system.
Yeah, and that is another way of looking at that is the measure of innate complexity versus the accidental complexity. You want to be able to make whatever changes you need in the innate complexity side. It's the accidental complexity where these things are coupled in ways that you wouldn't expect and shouldn't be the case when you think about it in retrospect. That's the kind of complexity you don't want to have, where you shouldn't need to worry about those connections.
When I think of coupling, the ability for teams to be able to build a feature, test, and deploy independent of each other. Usually I think of that coupling as, oh gosh, I'm reliant on someone else's functionality there and I need them to make a change over there, right? And that's what kind of shackles teams down. But what you said was so different than what I was expecting to hear. You said, no, I could actually, the lines in the system were drawn well. The systems were decomposed. Features were able to get done within the dozens of teams independently. The problem is that they couldn't test independently or deploy independently, which you said it actually shackled them so they couldn't act as 23 independent teams. They were basically acting as one giant team. Could you validate that being shackled by testing and deployment is as devastating as being shackled by inability to get the feature work done?
Well, addressing the last part first, I wouldn't say it is as devastating. Like you still have some of the coupling is broken up. The actual feature development is properly decoupled. But going back to what I've said earlier about distributed systems, that you can't really test except in production. You need to be prepared to deploy to production and test in a real world environment in a way that won't affect your users. Even though the new features for a given system were developed in a decoupled way, when you're working with synchronous systems that have a very nested service call graph, when you deploy your test version of the service, whoever is calling that service, in order for them to test it, will need their own parallel test environment or test deployment. And whoever's calling that service will need their own test environment, and so on, all the way up to the customer. Because the only way to test that your service and your changes to the service aren't going to break the customer is by traversing that entire call graph in a single synchronous call. Whereas the asynchronous event-driven services, you don't have to traverse the entire call graph in order to test that something is going to work. All you need to make sure is that whatever changes you've deployed, that your direct consumer is correctly going to consume those, and they don't have to worry about their own changes to their own contract that are also being pushed out asynchronously.
And so do I understand correctly that add new functionality, do I actually create a new topic for my consumers so that they can test on that new topic?
It depends on what your specific contract is with your consuming service. Maybe they know that you may be sending test or not quite production ready messages through a particular topic, and they're only picking out the ones that they identify and know about and ignore any V2 type messages or test messages. Or maybe you set up a separate topic because they're not ready for that and they can fully evaluate it on their own time. It's whichever works better on a case-by-case basis. I would say that the the rule of thumb would be a breaking change in schema would be something that you'd want in a new topic, and a non-breaking change should stay in the same topic.
Okay.
And that is a rule of thumb. You don't have to stick with that. The nice thing about event-driven systems like this, where you're working entirely asynchronously, is that even if you do mess up on your definition of what is breaking and what's not, it's not that big of a deal because you're already expecting to have some kind of delay in processing. It is going to be eventually consistent. If you need to do a rollback on your code because you made a mistake on your estimation of where to put it, it's usually not that big a deal as long as you know what your SLAs are and you're able to stay within those.
Got it. So in the case of a failure where a giant mistake was introduced, everything after the point of the deployment would be recomputed.
Yep, you could do that with a recompute. If your system is set up to process idempotently, it's not a big deal that you're handling all of these messages the same way. Most of the time, if you're talking about a breaking change, it's either going to process correctly or not. It's going to, most of the cases where you see these failures, it's just going to be a message that blows up the code on the receiving end. And you don't really need to worry about replaying. You just need to worry about fixing that one message or that particular schema.
Got it. So you don't actually have to do anything global. If you actually introduce a calculation error, then all you have to do is replay yours, and then that will trigger all the downstream recomputations.
Exactly.
Wow, that's so great. So clearly you did something that people appreciated, through your work at jet.com, through Panther and so forth. And it sounds like that the architecture you created replaced the dominant architecture, and is now the dominant architecture at Walmart. What did you do to bring that into being? Was it just passively you did nothing and everyone just noticed that it was a better way, and then they were the ones eagerly to drive it, or was it the other extreme where you had to bludgeon everybody into submission and everyone went kicking and screaming? I mean, so I guess I'm kind of imagining what the two extremes are. I imagine it's not one of those. Can you describe, what did you do that earned you the right to make such a huge change to the dominant architecture and eventually replace it?
With the merger of jet.com into Walmart, had the opportunity to show two systems that are doing approximately the same thing, but were built in completely different ways. You don't often get a chance in the real world to do such a great A/B test of two completely different ways of doing something and what the results would be. When we went back to first principles, starting with just merging the teams in the first place, what are we trying to solve from a business perspective? What are the business problems? And what are the non-functional goals, like in terms of resiliency, scalability, et cetera, that we will need to be able to meet in order to solve these problems? We're able to take the two existing systems from Jet and from Walmart, push them to their limits in the testing that we need to do, and see where they start to fall down, and make sure that everyone agreed, since everyone has already agreed that these are the principles we're trying to solve, or that we have, and these are the problems that we're trying to solve. It helps to get everyone on the same page that, hey, we can see that following this approach will produce better results in our 1-year plan and our 5-year plan than this other approach. So that worked really well to get the teams on the same page in the first place. Then with that, all that evidence we collected for ourselves in making the decision of which way we want to go, we were able to go to executives all the way up the chain to say, hey, here's the evidence that we found, here's what we're going to do and why. We want you to know that this is the approach we're going to take, because we want to come back to you once we've done this with the evidence that we've collected since then, and use it as you will to decide, hey, should we spread this approach to other teams as well? Mm-hmm. So we had a lot of good evidence from the A/B testing that we were able to do with the concepts that we were developing within our own two teams that were merging together.
And specifically the two teams, was it the inventory management systems?
Yes, the inventory management for jet.com and the Walmart.com specifically at the time. And since that was successful, we were given free rein to spread that to the stores, to spread it to international, and to use the same concepts in the Walmart fulfillment services where external parties are using Walmart's supply chain for fulfilling their own orders.
Was there a strategic mandate or a strategic desire to reduce the number of inventory management systems? Because I think I heard at one point Walmart had 3 inventory management systems, one for e-commerce, one for physical stores, and then plus Jet.com, so it's 3. Sounds like there's some downsides of having 3 of those instead of 1.
Well, in reality, the number is much higher when you look at all the international markets and the other non-Jet stores that were also under the Walmart umbrella. It's difficult to make inventory systems work by linking 2 existing ones together. A lot of other systems or other business domains, that's not as much of a problem. You can maintain the 2 parallel systems with their own, that are both working at smaller scale with their own teams, and that'll work okay. But inventory management, if by definition, you can only maintain inventory in one system at a time because you're trying to take reservations against it. You want to make sure that someone from Jet and someone from Walmart, if they're both trying to buy the same item in the same warehouse at the same time, only one of them should get it. You can't have 2 competing inventory management systems both do a reservation and do so successfully and make the customers happy. So inventory management has to be unified across, for a given warehouse or a given item, that has to be a single system.
Interesting. And when you don't, you either have inventory that can't be purchased by one. So you end up with too much inventory which can't be sold to certain customers.
Or the exact opposite, in that you only have one item sitting in a warehouse, but if you look at it from different perspectives, you'd be able to buy it from multiple sites all at the same time, and some customer is going to be unhappy.
Okay, right.
2 inventory management systems is lying to your customers. It's in many ways worse than having no inventory system at all, because at least you're not making that promise.
So let me share with you a story that I heard a couple weeks ago that is probably one of the most startling things that I've heard in the last couple of years. So I was talking to Dr. Steven Spear, and he tells me about a plant tour that he took in Japan with his mentor, Dr. Kent Bowen, and a VP of manufacturing from a big 3 auto manufacturer. And during this tour, the plant manager at a Toyota plant talked about how they were doing 60 line side store changes per day. So I didn't know what that was, but apparently, so in a physical manufacturing plant, it is where you get all the inputs in a given work center. And so they were making 60 of those changes per day. And this VP of manufacturing from the American Big 3 auto manufacturer says, that's crap. We tried to do 6 and to shut down the plant for 3 days. And it took me almost 2-3 hours to really understand why that was so interesting. But to me, it was shocking because it sounds so much like the people's reaction, my own included, when John Allspaw and Paul Hammond talked about how in 2009 they were doing 10 deploys a day. In fact, Mike Nygaard said when he first heard it, his reaction was they must be using some sort of slippery definition of deployment that doesn't match my own, because we do 10 in a year and that doesn't feel so good. But to me, this is just shocking. It sounds so familiar in the fact that clearly they're trying to do something by making these line side store changes. And some are able to do it very quickly and easily, and some are not. To me about your impression, me telling the story in a totally different context, right? Does that speak? Does that tell you? Is that speaking to you in any way?
That feels like it's the exact same problem. When you have too much coupling, your deploy is dependent on everyone else, and you have to slow down your deploys because of that. When you are able to minimize your blast radius and know that the exact limits for every deploy of what it could possibly affect, you become very comfortable in deploying much more frequently. And when you have systems that are event-driven, you know that the maximum possible blast radius is the single consumer that is going to be reading from your event stream. It's not going to go beyond that. And especially when you're using a lot of functional techniques that we've talked about multiple other times, you know that you're not going to be affecting your other features that you have in your own system. So both in terms of the systems you're impacting and the number of features within a system you're impacting, you know where what the blast radius is going to be, and you feel comfortable that, hey, worst case, I'll roll this back, and that is all that will have been affected at that time.
The expression on my face is actually one of surprise. So let's go into what those configurations are and some speculation that we have. So in the Toyota plant, Steve explains to me, is that that if you and I both have a work center, when we want to basically swap jobs, that all we would need to do, the primary mode of synchronization in a Toyota plant is a Kanban card, which basically is like an envelope with 3 fields on it. From, I need these parts from this person to be delivered here. And so if you and I if switch roles, then we swap the Kanban cards, right? And no one needs to know except for the loading dock. Whereas apparently in the system that 6 line side store changes results in shutdown for 3 days, everything goes through the centralized planning system, like this MRP system, that apparently are not entirely accurate. When you do these changes, you miss something, and routings are incomplete, and suddenly you have parts going to the wrong place, or parts that are not going to the parts going to where they aren't needed, and parts that are needed don't ever arrive. Does that surprise you?
No, the Kanban style system reminds me a lot of a queue, or a very queue heavy microservice architecture, where each person is analogous to a microservice in the software world, doing one thing with its input queue and its output queue, where it knows from where it needs to get the items and is focused on just that one thing. And that one service will know if its one queue for input is broken, or if it's not able to store its whatever the output is. In this case, some kind of material item. If there's no room there, it will know that, and each person is able to operate independently because of that decoupling. Whereas in a larger scale, centrally planned system, it's very similar to a monolith in the software architecture world, where when you don't have that, everything is very coupled together there. They do seem very analogous. You could draw the analogy. You have a central architecture or central architecture board that's trying to approve every single change that someone is making, and that you can't deploy that change from any small individual system until everyone has agreed on it and it has passed all the internal checks. Then only then do you deploy the new complete architecture that has this single approved change. That can really slow down agility. You're no longer working on contracts in between systems, but you are dictating that all the changes should go through a central configuration point where it can be approved. The comparison would be that each of these microservices that has just a very simple input contract and output contract, and each of the person or teams responsible for the services understands they just have to meet the contract, and they can figure out the best way for that service of how to make sure that those contracts, those SLAs, everything else are maintained. There doesn't need to be a central architecture board that's going to approve it sometime down the line and decide, okay, now that we approve, you can do it. As long as you give that responsibility to the team, say, hey, here are your SLAs, just make sure you meet them, and make sure that your business level contract is maintained. You figure out the rest. It allows the teams to work much more quickly and effectively independently.
Right. Got it. And then you're hinting at the other side, right? Which is that the architecture review board, you go through all that, the process, and yet sometimes they can miss something, and then everything's come crashing down, just like as we've explored in the past. This is so great. So in your talk, you didn't have time to go into this, but you had given me some advice. I had this system that's been working for 4.5 years, and I had described as having so many problems with it, failing in all sorts of strange ways. I'm going to just read to you this testimonial on how your advice to me worked. So I asked Scott Havens for his advice on how I decouple a bunch of components that write to a database through a terrible Rupee active record app I wrote that interfaced to a Python that someone else wrote. And he told me to move it to event sourcing with PubSub. At first, I couldn't quite believe this was practical. PubSub for such a simple app. But then I took your advice and I was blown away by the results. Suddenly, two components that used to be tightly coupled together with all sorts of weird failure modes where things couldn't be written out correctly just disappeared. I was stunned that in my very simple case, I managed to reduce the code size by 90% and delete entire portions written in Python and Ruby, and all that remains is a very small portion I've written in Clojure. So, I guess even reading this, I have a little bit of disbelief. So how can even simple systems suffer from problems like this? To me, it just seems so unexpected. Is there an easy answer to that, Scott?
I think the keys is to realize that any system that you're trying to develop that's solving some kind of business problem is always event sourced or event driven in the business domain. All businesses and all problems really have a series of events that happen. The question is, do you want to make that explicit and understand those events, or do you want the series of events to just be implicit in the code? When it's implicit in the code, it makes it very hard to debug because it's still there, and that's what you're inherently trying to solve from the business side. But you're not going to be able to get to the events themselves and understand the flow of events through the system until you make those explicit. So really, every system is event sourced. The question is, are you choosing to have that in code and store them, or are you choosing to make it hidden in the business logic and throw the events away so you can never recreate them? So that is one difference that you see.
And I think, in hindsight, what really helped the problem was that side effects were treated very differently. I was processing events in a very side effecty way that was very prone to failure, and I saw modes of failure that I could never have dreamed up of when I wrote the code. Is that part of what you're saying?
It's not the same part, but that is another aspect that is just as important. When you have a system that mixes your side effects with your business processing, it means that the correctness of your business logic is dependent on all of your IO always being exactly correct.
Right.
And when you have them intermixed, any failures in the IO side or any mistakes you've made in your IO portion are going to affect the correctness of your business logic. When you design your system, and again, I'm going to call this in a functional manner, where all of the business logic is happening, where you have your command that is completely immutable, you have a pure function that takes the command in current state and computes a new output state or a new set of output events. And without any interaction with the outside world, you're able to prove that that business logic is completely correct, at least in terms of the code of what it's trying to do, what the business problems it's trying to solve. Then when you have finally at the last stage your output, whether that is a state update or your set of events, and only then do you store it to your data store, whatever that is, or put it in a queue or whatever you choose to do with it, then you only have to worry about, is the IO correctly saving it or not? And that's much easier to solve than, is the business logic reading the right thing and completely able to recover from any IO failure with the right data and have the right state and be applying the right change to the right model at the right point in time. It just becomes way too complex to be able to handle every single error case compared to, here's my business logic, and then is going to be the IO. Once you separate those problems, it makes each of them significantly easier to solve because they're no longer so interconnected that it multiplies out all of the possible problems.
Right. And by the way, it was that experience that really took my understanding of functional programming communities, pushed the side effects to the edges, and reduce that surface area of the testing the side effects down. Right, it's like you don't actually really have to test that the database will write. Right, in general, you can almost depend upon that. What you really want to do is isolate the testing to the logic, right? Which was such an aha moment. Gene here. Okay, a couple of quick things. One, I love how eloquently Scott spoke about the value of being able to make local changes and be able to test them locally without having to worry about how the rest of the system works. This is so consistent with the themes of encapsulation from Dr. Gail Murphy. And this is, of course, the heart of the first ideal of locality and simplicity that shows up in the Unicorn Project. Number 2, one of the things that Scott really helped me understand in this interview is how he thinks in the way he does. I had mentioned in my introduction to him in his DevOps Enterprise presentation the quote from the French philosopher Claude Lévi-Strauss about whether a tool was good to think with. Scott has explained to me some pretty amazing tools to think with. We talked about currying and function composition in the first break-in, and Scott mentioned another one, idempotence. This is the property that an operation can be executed multiple times without changing the result. I was familiar with this term in the context of distributed computing, as in an operation is called idempotent if it can be executed more than once safely. This can be a very important property for side-effecting operations, like databases or file systems or network calls. So under a certain condition, you may want to make sure that certain operations, such as adding or deleting an element, can be performed in a way that is idempotent, so that you can survive network issues without corrupting data. But while researching this, I discovered that this term also has a more fundamental mathematical connotation. For instance, multiplication is idempotent only for the operations of multiplying by 0 or 1, and addition is idempotent for only the value 0. I'll have a bit more about using these in another break-in. Okay, number 3. Scott talked about how if you have more than one inventory management system, you can't actually take reservations accurately against it. Holy cow, I had no idea that this was actually the case. I know of many organizations that have multiple inventory management systems, and apparently there is a cost to this. I suspect that there's so much value that could be created if organizations bit the bullet and unified their inventory management systems. Number 4. Scott, in his DevOps Enterprise presentation and in this interview, referred to a toy application that I had written. This is actually an application that is super important to me because it provides telemetry on how books are selling on certain e-commerce platforms, which is actually a critical capability when executing book launches. Because book launches, like any activity, is one where it's important to be able to see what you're doing. So this program started off as something that I worked on with Tom Limoncelli, author of the amazing Cloud Administration book, and this was one of my first recurring workloads in the cloud. I eventually took this project over and then proceeded to turn it into a Frankenstein monstrosity. It was made up of Tom's amazing code written in Python, my unreliable code written in Ruby and Active Record, which would write values out to a database, send emails, and Slack messages. The code that I had written was incredibly unreliable. It would fail for so many reasons, the least of which was being occasionally blacklisted by those e-commerce sites. Over the years, I eventually was able to stabilize it. I eventually rewrote the whole thing in Clojure, which made it much smaller, and I was amazed at how much smaller it got when I rewrote it to run primarily on Google PubSub, which is very much like Apache Kafka, which Scott used. You heard the testimonial I gave about doing that in Scott's DevOps Enterprise talk. If you're interested in how I did this, I gave a fuller experience report of this at the 2019 ClojureCon conference. I will put a link to it in the show notes. Okay, number 5. Let's talk about the definition of side effect. So according to Wikipedia, a function is said to have a side effect if it modifies some state variable outside of its local environment. That is to say, it has an observable effect besides returning a value. In that entry, it actually talks about maybe the more useful notion of referential transparency. So the absence of side effects is a necessary but not sufficient condition for referential transparency, which means an expression, such as a function call, can always be replaced with its value. So this gets to the notion of a pure function. So a pure function has referential transparency. Given a set of inputs, a pure function always returns the same thing. So a non-pure function is when you do a network call or when you write to disk or even read from a disk, because the result may not always be the same. In fact, calling the getSystemTime function is not pure because it is different every time you call it if the granularity is small enough. And so when I say side effects, what I really mean are non-pure functions. Which gets us to number 6. That took a lot of words to describe a pretty simple concept. So I think Eric Norman has a much better definition, which he proposed in his fantastic book, Grokking Simplicity. Basically, everything can be boiled down to either data, calculations, or actions. So data is inert. So think about a string, a number, a data structure in JSON. Ideally, you can't mutate it. If you want to change it, you have to create a new set of data. Then you have calculations. Calculations operate on data, and calculations are always pure functions. So these can be things like adding, subtracting, capitalizing, map, filter, reduce. And then you have actions, which are any operations that aren't pure. So this is making a network call, writing or reading from disk to a database, getting the system time, sending an email, posting to Slack. Eric Normand was recently on a book tour, and he did so many great interviews on this topic, and I'll point to a couple of them, which I think are incredibly instructive. I love this reframing of functional programming concepts of everything being data, calculations, or an action. Which gets us to number 7. So many of the problems that I described in my book e-commerce application was due to the terrible way I was handling side effects. Deeply nested calls where I was fetching a result from an API, writing it to a database, posting it to Slack, generating a graph. And so when something went wrong, it's usually deeply inside of a call stack. And when my program blew up, it's just not clear what went wrong or how to better handle that error. So much of fixing that application was pushing side effects to the edges, pulling apart these individual I/O operations and isolating them. And that way you tend to have very simple cases when you're doing I/O, and the tests are really about the calculations, not about the actions. And this pattern is often called creating a functional core with an imperative shell. The notion that you want as much written in a functional style based on calculations and data, and you have all your imperative actions at the edges. Which gets us to number 8. There is an amazing series on this in one of my favorite podcasts, which is the Functional Design in Clojure podcast by Christoph Newman and Nate Jones. I loved all 100 episodes that they did, but one of my favorites was when they designed a Twitter scheduling system. These are episodes number 21 to 26, where they go through the process of separating the logic and the I/O, and how you write better tests, and the patterns that emerge. It was so dazzling to listen to, and what's so interesting is that what they eventually evolve into is a CQRS or event sourcing system, just as Scott is describing. It's just brilliant. Okay, with that, let's go back to the interview. I've heard this a couple of times before, that when you, in CQRS, it's sometimes difficult to sort of comprehend what the call graph actually looks like. Can you talk about whether this problem is just isolated to me? And I understand that you've been doing some work in this as well.
The issues that we have seen in switching to these event-driven asynchronous architectures, the synchronous call graph of all of the services that you see in, or that we had at Walmart before, and that you see in a lot of places where you have these nested RPC calls. The downside of them, as we've talked about, is that they're all coupled together temporally. You have to have all of these working correctly within the same call with no failures in order to have a successful response to the customer or whoever's hitting your end API. That is also a positive in terms of being able to understand what happened, in that it's a fairly well understood technical challenge of being able to write down that service A is calling service B, which is calling service C. It creates a tree of calls that is, you can write down and understand that if there is a problem that happened in this call, it's going to be in one or somewhere in this tree. You're able to understand that it can't have been affected by something that happened yesterday, and it's not going to have an effect on something that happens tomorrow. It is very well temporally contained. So yes, you have to deal with the latency up front from an operational perspective, but you're able to limit, or when you're looking for problems, you're able to focus where you're looking to just that single call graph. In an asynchronous system, the big advantage is that you have been able to spread the responsibility temporally, smear it over the last seconds, minutes, hours, so that the customer doesn't need to know how long it took to compute all of these things, and that the testing was able to happen at different stages in advance. That also means that if you're trying to examine a system in production, observe what happened with a particular call, you're not going to be able to reconstruct the causality nearly as easily. The response that the customer gets on a particular call, when it's looking up something in a key value store, the problem, it probably isn't there. It is in how that value is calculated, which could have been, even months ago. And understanding that causality graph becomes a lot more difficult.
And you said that this is an area that you've been researching or doing something about?
I've been looking into it because it's one of the biggest problems that we've seen in these asynchronous distributed systems. We've seen a lot of intersection between distributed tracing desires in observability and synchronous systems, where because you want to understand the latency at every point in all of these calls and how all of these different services are connected together, distributed tracing has come into existence to help with observability, where you're able to see the latency at every single hop in the service chain and be able to dig into, maybe this is a database call that was a little bit slower. It really helps with observability concerns. From another perspective, from the business domain perspective, especially coming from supply chain, we wanted to understand the flow of goods through the entire supply chain over time. And this doesn't seem like a technical problem. It seems much more like a business problem. But they really end up being very deeply connected when you want to be able to prove that something arrived at the warehouse several weeks ago and then was moved to a different part of the warehouse. And then an order was received and we wanted to ship that item and we packing it up. All of these business events that are happening over time, you want to be able to prove that you know where everything is in the entire supply chain at any given point in time. You want to be able to know that when the downstream effects of any single change that you requested, and you want to be able to trace back the graph of all causes of a particular effect. If you see that this item was moved from warehouse A to warehouse B, you want to be able to say, oh, let's look at that item's history and see that, oh, it was moved from this warehouse because of this request. And that request was put in by this person at this point in time 2 weeks ago, and be able to trace back all the way the entire history, not just within a single system, but across systems. All of these business problems of wanting to audit every single change that has happened end up really correlating very strongly to wanting to be able to trace back all of the messages and events at a system level. What we want to do is marry the concerns of distributed tracing that you see in the synchronous systems, where you're seeing the call graph over time, and get the causality graph that will help you in understanding your business domain, looking at or to build a graph of causality across all of your systems, where you're able to prove no message was lost. You're able to identify the time in between each set of events and understand that or make sure that you're hitting all of your SLAs in an event-driven system, and be able to derive a business understanding from looking at your message flows. This is an area that I'm not the first person to identify that there is a problem here, but there aren't a whole lot of good solutions yet.
And can you help educate me on, is this a big problem and why? Why is this a problem worth solving?
By the time you get to the point that you want to make sure that there are no mistakes in the real world handling of whatever you're doing, making sure that every last item is going to get to the customer within the right amount of time, that you're always going to be fulfilling your promise, it becomes very difficult to make additional improvements. And you're not going to be able to make improvements in your fulfillment rate without knowing where you're failing. We're already at a point where you have 2 or 3 nines of correctness on getting the item to the customer within a certain period of time. But if you want to address that next 9 of accuracy on availability and fulfillment rate, and you want to figure out where can we cut down the most on time on the processing steps to change it from next day shipping to same day to 2-hour, 1-hour shipping, identifying where are the slow parts in the chain and where are we making mistakes, where are we dropping messages or taking too long to process. You need to be able to trace every single message, not just sample some messages, and you need to be able to audit that every single one is happening with the latencies for each of those to be able to graph the entire thing and drill into, hey, here's where the problem is. Without that information, you're not going to be able to make any improvements in the system.
The Idealcast is produced by IT Revolution, where our goal is to help technology leaders succeed and their organizations win through books, events, podcasts, and research. This episode is made possible with the support from ServiceNow. Take the risk out of going fast. If you need to eliminate friction between dev and ops, head to servicenow.com/devops to find out more. I was listening to a presentation by Art Byrne. Yeah, he's a lean pioneer leader who got so good operations manufacturing at Wiremold. Part of their acquisition strategy was to actually acquire underperforming plants and create greatness within them. It was an astounding story. And listening to the video, he actually talked about something that I just didn't understand. I've heard Steve Spear talk about the miracle of Toyota and that people keep thinking it's about manufacturing. But he said it's nothing short of miraculous, that a Toyota plant can create, generate 4,000 or 5,000 cars per day, defect free, and just all the choreography it takes to get parts to where it needs to go. And I kind of accepted that. I thought I intellectually understood it. But then in this Art Byrne talk, he talked about going to one of the Toyota suppliers where engines are being sent in lots of 4, a couple of times a day. And him asking the driver, how many times have you been late delivering an engine to a Toyota plant? And the driver said, once 11 years ago in a snowstorm. But, we ended up putting it on a helicopter and getting it over there. And, transiting multiple hours, being this convoy of trucks, it made me realize I did not fully internalize the scale of the miracle that's occurring every day to support that rate of production. I suspect you've seen something similar in terms of just the volumes of flow and the incredible choreography it takes to actually ship things that you speak so eloquently about, to get it so that customer gets what they ordered. Can you describe to me maybe the scale and your awe of the system? I mean, help me understand the vast scales of which these organizations operate in.
Oh, I don't think that I can even give a really good picture of what the scale is. I think that is the point of what makes this whole thing, or everything about this so difficult, is that no one can really put in their head the entire flow at the same time. Like that goes exactly to the point of why we want to break things up so that we have limited blast radius on changes in the first place, because no one's going to be able to keep in their head the entire thing. Now, that said, when you're dealing with even just something that's just a fraction of Walmart's business and just the supply chain side, you're dealing with, last count, 4,500 stores in the US, each of which have somewhere between hundreds of thousands of items in each one. You have hundreds of warehouses around the country and hundreds more around the world. You have, I don't even want to count how many different manufacturers of all of these items that you have to understand where they are in their process and how soon they'll be able to get these things to you. All of the potential possibilities for the transportation networks, from distribution centers to fulfillment centers and stores, of how long it takes to get an item off the shelf in a warehouse, packed into a crate or into a box, put onto a truck, know exactly how long it's going to take that truck to get to the next place where it's going to be put on a shelf in a store or it's going to be shipped to a customer. And the advances we've made in being able to analyze the entire workflow across all of these different stages, where you're dealing with thousands, if not millions of people working on these systems. It used to take weeks to be able to get something from A to B across the country and do so on a regular basis. And now we're able to do 2-hour fulfillment in most markets on any good. And this isn't just Walmart. Amazon, it arguably was doing that even earlier. And But the scope is amazing, and you only get that from being able to collect all of the data from all of your hopefully independent systems and see how long it takes to do all of these different steps without necessarily knowing what all the steps are in advance. The point is, you need to be able to collect the data, and without having the full understanding of what you're going to be looking at, be able to derive that understanding just from looking at the event flow across all of these systems.
Can you describe a moment in either Jet.com or Walmart where that you just found particularly that evoked a sense of utter awe that in terms of seeing the effects of what you helped create?
The first story that comes to mind is when I was asked to do very rigorous scalability and performance testing on the what was at the time going to be the Panther system, where we needed to make sure that it was going to be able to handle the scalability of what would eventually be Walmart's scale. Nothing was public at the time about the acquisition, but we had a sense of that was what the skill that we were going to need with that. And I said, okay, this is the budget I'm going to need to be able to do these tests, to be able to scale up for this period of time. How is that going to provide the data that we need? And I was told, no, we need to go even bigger. We need to really be able to prove that we're able to do this for a week straight at maximum scalability, and that we're not going to have any problems at all. Just a really in-depth soak test. And the budget that I had figured was going to be, and again, we're working in a startup at that point. It was a well-funded startup, but still thinking about money and not wanting to spend too much. I was thinking, okay, this is going to be super expensive. We're going to drop 10 grand on a single performance test. But that's the kind of thing that's important. And to have the answer come back and say, no, you need to be thinking an order of magnitude higher than that. We need to spend $100,000 to $200,000 on scalability just to be able to prove that we're able to do that. That amount of money on a single performance test was beyond anything I had done at that point.
And did it find anything interesting?
Well, it was interesting to me that everything worked great. I was super thrilled about that, obviously. But it really said a lot to the fundamentals of the architecture and the designs based on that architecture, that we were able to handle that kind of scale, even if it was just in not quite a production environment, but using production level data that had been replicated to that level of scale. I was really happy with that.
That's awesome. Congratulations. So the main effect was like generating a lot of heat. $250,000 spent heating up a data center somewhere.
But I would still argue it's more useful than using all that money on blockchain computation. But
right. That's awesome. All right. And obviously it was the assurance that created is even orders of magnitude even more valuable than that. Okay, Gene here. 2 quick things. 1, I love how Scott described the dizzying business problem that arises when you don't have perfect inventory information at all points in the supply chain, whether it's in a warehouse, whether it's being picked or packed, whether it's in transport, being unloaded or shelved at another warehouse. I had mentioned that amazing presentation by Art Byrne. I'm going to put a link to his 2013 presentation that he gave at the Lean Summit in the show notes. It's just such a breathtaking example of what mastery of a given domain looks like. And the reference to the dizzying level of choreography required to deliver engines to a Toyota plant will be in another link. Number 2, Scott had mentioned the $250,000 bill of that huge performance test that may have been critical to the Walmart acquisition. This was definitely a bet that paid off because in 2016, Walmart acquired them in a $3.3 billion acquisition. $3 billion in cash and $300 million in Walmart shares. Okay, back to the interview. I feel like 10 years from now, all these philosophies and techniques that you talk about will be far more mainstream. And I think people will actually point to your presentation as one of the reasons that made that so. And I think one of the things that you talked about was especially surprising to me was about the small teams that actually created this. You just talked about the Panther written by essentially 5 engineers. You talked about how a new developer with very little experience in F Sharp was able to deliver a feature that halved inventory reject rates by half in only 3 weeks. And this is stunning to me, right? Because I mean, maybe just but exaggerate to make a point. Many people would say, "Oh, this is all well and good, but our organization is too stupid to use these principles. People aren't smart enough." and I think you went out of your way to really suggest that that's not the case at all, right? Can you talk about what it was like to not just be an architect, but essentially, you're leading a team of engineers. What was it like to onboard new engineers and get to the point where they could be productive and generate valuable features?
Bringing on new engineers has always been fun for me. So many of them have been trained in more object-oriented techniques and in more classical architectures, the N-tier architecture with your single database and maybe your set of web servers and load balancers, and haven't really had the opportunity to work in an architecture like this that is cloud native. And now a lot more people are accustomed to that than they were 5 years ago when we were starting this project. But even so, nowadays, a lot of people still haven't fully internalized the changes that you need to make to how you design your systems for the cloud. But it's always been fun bringing on new people and saying, hey, the only change that I want you to think about for right now is a complete separation of your domain logic from your IO. Let's start with that. You can do that in any language. Don't worry about any of the cool stuff in this particular language. You don't need to know what computation expressions in F# are, or even know the definition of a monad, which so many people always get hung up on things like that in functional programming. Like, no, those aren't the important parts. Just focus on doing your business logic right here, figure out what the result is that you want, and then save it off. Start with that. And that comes pretty easily to most people. And that is just the start of the change in mindset into thinking functionally, making sure that you have that purity in how you're developing your code. That is while it's an easy change, it ends up being super important in that they can then see that same principle applied in larger and larger scales. And when they see, why is the system built this way? Oh, it's to have that separation, to maintain that purity, and everything builds up from there. The system as a whole, it ends up looking like just a larger version of that much smaller function. So that ends up being really the first thing that I do with bringing people on. And maybe I've been lucky with the developers, all the developers that I've hired or gotten to come into the teams, but everyone's been able, when you pick that part up first, been able to pick up the rest very easily because of it. It's really just that quick switch in the mindset.
So suppose I'm this new engineer that you've hired, and I'm being handed a portion of the project to have delivery reject rates, and I've never done F#. I mean, can you describe what my first week might be like? How do you orient me, and like what does my context look like when I open up my laptop and try to start to prove to you that I can actually do this, or prove to myself that I can do this?
The first thing that I will do is explain the design of a system that exists right now and how it takes in a message off of a queue. If it needs to, maps it to the internal domain model. It does its computation. It saves it to a data store as the event that is the result of the computation. And that event will get emitted downstream automatically by the change data capture that's already in place. Explain, this is the model we want for all of our systems. At that point, they usually get that, okay, if I follow this model, what would my next feature look like? Is it an entire new system that runs in parallel, or is it just a modification to the business logic? And usually, if they're just starting out, we just want to add one small feature to the business logic, but we're able to point to this is where that should exist for the systems you're looking at. And the structure is similar across all of these systems, so they know to look in the same place, and it's following the same pattern. because a pattern that happens naturally when you are separating your pure business logic from your IO. It's always going to be in the same place that you look, whether it's system A, system B, system C, or if the change that they are going to make is to the IO side of things, they know it's going to be in the IO section of the code. And it becomes pretty straightforward of where they are going to need to look just based on the scope of the feature that they're going to build. That's the blast radius part that I mentioned earlier. They don't need to understand the entire system up front before making changes. They don't need to understand how this system interacts with other systems. They're able to be confident that once I've identified the place where I think I need to change, they're correct. That's all they're going to need to change, and it's not going to break anything else.
And so just to react to that, I'm smiling because I'm like, oh my gosh, that sounds great, right? I mean, you're probably pointing me into it. It's going to be in this function or this module. I don't have to deal with I/O, and it's probably going to be a computation. It sounds wonderful. And so I'm also assuming that you'll give me like an input data set and some idea what the output should look like, or here's what the output looks like now, and the output probably is going to look like this. I mean, that also helps kind of concretize the problem that needs to be solved.
The existing inputs and outputs are all explicit in code because you're not dealing with a randomized JSON message coming from an API. Like, here is the part of the code that explicitly lists every single possible input message that the system will process. It does map from some external data source, a queue or the like, where the messages are going to come in, but you don't need to worry about those. You only have to worry about your explicit set of input messages. And on the other end, on the output side, your explicit set of output events. Yeah. You know what those boundaries are. And as long as you're dealing with the pre-existing set of input and output messages, there's no possible way for you to break any other system, as long as your business logic is correct.
It's strange. I might be inferring too much here, but that sounds so fun. I mean, when I think about my worst episodes of programming, I mean, it usually has to do with side effects. I remember writing like a multicast driver for Windows 3.1. I mean, it was all side effects in a treacherously dangerous system, right? They usually blue screens a box, right? And you're just trying to understand, how does the underlying system work, right? Windows 3.1, interrupt drivers and registers, like, not fun. But when you're dealing with these computations that can be easily tested, right? And the worst thing that can happen is a failing test. I mean, it just sounds fun, right? Because you're in the business logic. Am I deluding myself that's kind of how the experience feels like?
It really is. It makes the business logic part so straightforward that you can have your product person review your code and make sure that, hey, this is exactly what we expect the output to be. This is what we want the result to be. The code looks good here. It's when you've taken out all of the I/O, you've taken out all of the bootstrapping code, everything that we think of as engineers that you need to have in order just to make the system run. You've pulled out just the core business logic into its own very pure code that people with minimal programming experience are going to be able to read and understand. The I/O is, because it's completely separated, you're able to make your changes to the I/O as necessary without worrying that you're going to affect your business logic. It's either going to keep correctly saving or emitting the events, or it's going to stop working. And you'll know pretty quickly, but you're never going to get straight up inaccurate results. When you have that binary of working or not in the I/O layer, it helps you understand that your blast radius is very limited and you'll never have incorrect result.
Do you find that engineers are having more fun?
Oh, first I'll limit it to me. I feel happiest in a role when I am being productive. I am solving business problems. And I think most engineers feel that way. Yes, more money is nice. Recognition is nice. But if I'm not actually having an impact on the business, I feel like everything I'm doing is just going into a black hole. With systems that are designed like this, where you're able to focus on the business logic changes, you know it's very easy to have an impact on the business because you're able to measure exactly that, hey, I added this feature to the business logic. I was able to test it fully. I know that I don't have to wait on anyone else in order to get it into production. And you can look at the before and after on whatever metrics I'm collecting and see that I actually had an impact. You're able, when you don't have to worry about your overhead code or spend a lot of time on your bootstrapping code or making sure you get the IO just right. You make your change to business logic, you push it to production, you're good to go. You've already made an impact. It's very fulfilling for me.
Gene here. I want to quickly describe that experience working in the Windows 3.1 multicast networking group. That was in 1995 and was what brought me to Portland, Oregon, which is where I still live. It was a summer internship working with Intel while I was a graduate student at the University of Arizona. It required implementing the network multicast protocol for the TCP/IP network stack in the 16-bit Windows operating system. For my temperament, it was like the worst job ever. It probably didn't help that I wasn't very good at it. My memory of that summer was constantly getting the blue screen of death on my dev workstation because of memory address errors. In hindsight, it is obvious that one of the main reasons is that I didn't understand what a segment pointer was. So in the 16-bit Intel x86 architecture, you had near pointers and far pointers. Basically, if you referred to any memory address that wasn't in your current 64K block of memory, you had to use a far pointer. And if you didn't, you'd end up with a segmentation fault and you would get the Windows blue screen of death. I think I spent over 2 weeks trying to figure out why this was happening to me, and the only tool I had was a hardware debugger. It was something you plugged into your PC, and it had a thumb switch that would bring you into a hardware debugger and let you inspect the memory. Reboots and the feedback loops were so long. I remember that for certain weeks, I was working late into the night every night, basically seeing blue screen of death after blue screen of death. And by the way, this is what is so amazing about having flat address spaces. You don't have to worry about segment pointers anymore. And this was only made possible by 32-bit programming that came in with Windows 95 and Windows NT, Linux, and later Mac OS. I cannot overstate how much this simplified programming. For a while, I thought I wanted to do operating system work. In hindsight, that's the exact opposite of what I would like to do. I just want to work in a nice dev environment with the entire environment created for me, and I just get to work on the business logic where the worst thing that can happen is a failed test. It's the ideal where you get fast feedback on your work, and you get to work safely within your module with very little changes and side effects happening outside of your module, just like how Scott described. Okay, back to the interview. At Moda Operandi, you had an opportunity to take these same principles into a Ruby on Rails code base. I'd love to hear any reflections on that. And my last question will be when is CQRS unsuitable? Can you talk about anything about your Moda Operandi experience? What is it like to tackle a Ruby on Rails code base? And to what extent is it applicable there?
I would say that it's pretty difficult to follow this style on a pre-existing Ruby on Rails application. It's not what Rails was designed to do. It's designed very much for storing the values directly to the database, a lot of updates in place. We spent less time on trying to put in new features in that code base versus extract the features out into separate services. If there's something that is a basic part of a feature that was already in place in that code base, we'd write our new microservice that we were able to deploy completely separately, test independently, and with that in place, then make the change to the Ruby monolith to, instead of making this call in its own code base, to either emit an event or call out to the separate already completed service. So we were really following a strangler pattern there, where we would write code following a new model that would replace the existing part and then cut that off and over time cut down on the monolith that existed there.
What did you write these new services in?
I was lucky to get a team there that was already pretty familiar with functional programming, which made me happy. Their background was mostly in Scala, and I don't really care which language we're doing it in, as long as we're following certain principles. So we did all of this in Scala.
And were there any surprises in that journey or something that you're most proud of?
I was really happy that we were able to get the fulfillment rates up quite a bit. There were the existing code base, because it was doing a lot of updates in place and didn't have as many unit tests as it did integration tests, was not able to fully cover all of the potential business cases. That happens a lot. Startups, you get the code in place that is working, and you have to move on to your next problem. It's more important to get some of these features in place early on than to prove that if you add more warehouses down the line, that if you get to the point that that's a problem, that you're dealing with lots of warehouses instead of your single one, then you should be pretty happy that you're able to get there in the first place. But then it did lead to problems where we weren't able to test exhaustively all potential inputs and outputs to the business logic. And so 5, 6, 7 years later, we stumble across this problem because we were doing inputs in place, and now we made a change in one part of the system, and it ended up having impacts in other parts that we didn't expect. The blast radius was not particularly contained. So as we were able to identify these parts of the code handling supply chain issues and extract them to an exhaustively tested microservice, we were able to eliminate a lot of the code errors that were putting in incorrect inventory values in these corner cases, or calculating the transportation times incorrectly, or all of these different supply chain potential code bugs, and get our reject rates from, I shouldn't give exact numbers, but much better reject rates than we had been seeing before. When the customer has requested an item and expects the item to arrive by a certain point in time, and we end up not being able to fulfill that promise. You want that number as low as possible, or the inverse of that being the fulfillment rate and the perfect order rate, that we've been able to get that order to the customer on time without making any mistakes in which item we selected or damage to the item or anything like that. So
and does late contribute to reject rate?
For reject rate, no. But reject rate is a portion of what we call the perfect order rate, which is all inclusive. It's really the best descriptor of the customer experience, where they were expecting the right item undamaged by a certain point in time, and making sure that we get that order to them perfectly, fulfilling all those expectations.
So one of the things I'm starting to suspect is that it's really important at the highest levels of leadership to understand the importance of good architecture. And often I feel like there's a gap. In other words, many big decisions are being made not properly informed by architecture, or maybe not with the recognition of that they don't have a good architecture and they need to invest in one. What advice would you give to business leadership? How do you help leaders get that aha moment? Right, to care about the things that you care about? What advice would you give to someone who wants to replicate the journey that you've had?
I think that is an excellent question, particularly since I don't know if it's reasonable for executives who are focused on making sure that the technology organization as a whole is not just solving some business problems, but solving the right business problems. But it is important that they are measuring the right things from their technology organization. You're very familiar with all of the software delivery metrics that, in talking about making sure that the lead time on changes that are getting to production, that you're measuring that you're measuring the number of successful deploys at a time. I would say that executives need to make sure that they're pushing those metrics down to the front level managers, and that the managers let the teams know that that's what they're measuring, not just number of commits or number of bugs that are filed, but that they're measuring these particular metrics. And then the executives need to be able to listen to their engineers, their architects, who say that these architectures will be improving these output metrics, these delivery metrics. And over, maybe in 5 or 10 years, there are going to be new advances in architecture that we have no idea about now. But you should be able to test these architectures in your own teams by saying, hey, if they are going to improve these metrics, these delivery metrics, then let's do that. Let's try it, see how it works, and see if it actually makes our teams better in the long run. It's not a matter of going with a particular architecture. It's a matter of being comfortable with new or different architectures that may have real world differences in your productivity, being able to listen to those people who are saying, hey, we're going to see these differences in productivity, but making sure that you are getting your teams to measure that productivity rather than just saying this is the next new cool thing.
So I heard the accelerate metrics of deployment frequency, change deployment lead time, change success rate, mean time to repair.
Yep.
And you're saying that there's a certain sufficiency there. And I also heard you say if there's a gap, you have to be able to create room for architectural experiments. And I think I'm hearing with a promise that could promise, orders of magnitude improvement in those, and just making room for that experimentation. Did I capture the salient aspects of the answer?
Yes, it's the experimentation combined with making sure the promise is fulfilled.
Yeah.
You just doing a cool thing because it's new and cool isn't enough.
Yeah.
You do the cool new thing because it has a promise that it will have better results. And so you should be able to measure those results. And that should be something that is upfront whenever you are pushing an architectural change that could be affecting a bunch of people. You should be able to know what are the expectations from this. At what point should we see these results? What do you expect to see and why? And make sure that your engineers and architects are answering those questions before they do the experiment.
I'm 3.5, 4 years into functional programming, and I still have a loose grasp of understanding of category theory, monoids, semigroups, functors, applicative functors, monads, right? I mean, what do people need to understand? It's clearly a precise way to think that I certainly appreciate, but there are times when I wonder, will I ever get there, and how much energy should I invest in understanding these concepts? What advice would you give me on that?
I would say the vast majority of it is irrelevant. It's useful if you are wanting to debate whether a particular feature should be added to a language in the most effective way that has the broadest impact for the least amount of changes to the syntax. In general, though, I've found that most developers who are working on line of business applications or regular websites, using all of the terms from category theory that you were listing earlier isn't going to help them build better software. What's going to help them is to see examples of here's how to do error handling in a way that doesn't involve throwing an exception and catching it somewhere up the stack, but by having a result type that has two options: your success result that has whatever that result is, or your failure result that has an error message included in it, and returning that single result type as opposed to throwing exception. Giving examples like that and showing how they can be useful in the real world ends up being much more important in terms of getting new developers to be productive in a language. If they want to go off on their own and learn about monoids and monads and applicative functors and just all of the fun category theory stuff, great, let them, and they'll get a better understanding of why these things were designed the way they were in the first place. But that's not going to necessarily help you build a discriminated union that covers all of your potential inputs and make sure that you're exhaustively testing all of your business code.
Okay, Gene here. I love what Scott just said, saying that category theory is probably overrated and not critical to learn to be able to write better, simpler programs in a functional programming style. Okay, so number one, it occurs to me that one of my biggest aha moments in functional programming is not my shaky grasp of category theory. Instead, it is the notion of algebraic thinking, which is also described brilliantly by Eric Normand. He has this amazing podcast episode called Examples of Algebraic Thinking. He gives an example of building a video editing program comprised primarily of pure functions that operate on videos. So you can split or trim them, you can concatenate them together, so that for any given time t in a timeline, you know what frame should go there. You don't mutate them in place, but instead you transform them, composing these functions and operations together. It's just a great way to think about solving problems. And he gives two other examples in that podcast episode. And incidentally, when you're doing this, when you're using these tools to think with, you're actually using the properties of monoids, where the order of operations and grouping don't matter. It's pretty awesome. Which gets us to number 2. I've also been enjoying Adam Gordon Bell's podcast called Co-Recursive. There's an episode where he interviews Sam Ritchie, who discovers that you can actually do certain types of searches and counting in hyper-log time if you're willing to put up with some inaccuracies because of a property of another thing that comes from category theories called semigroups. I don't actually claim to understand this, but it does show that there are some pretty amazing things you can do if you understand some of the mathematical properties. Which gets us to number 3. Despite all this, I love what Scott says. You don't actually need to understand category theory, which I don't even want to try to define here because I can't, in order to use functional programming to get some of these amazing benefits that have been mentioned throughout this podcast. To build things in a simpler, faster, safer way, which also makes us happier. Which gets to the last point, number 4. Maybe to prove this, Dr. Adam Grant, famous for many things, including one of my favorite books, Give and Take, tweeted this out earlier this year. He said, "Coding is more about communicating than computing. New data, the best predictor of how quickly people learn to code wasn't math or cognitive ability, but language aptitude. In other words, math skill was almost irrelevant. Coding is a mastering of language." And he points to a Nature article that explored this. Pretty great. Okay, here's Scott to conclude the interview. I love it. Scott, I got to tell you, I've learned so much from you over the years, and I've had so much fun in these interviews. Thank you so much. I love the fact that in our talk, you said one of your missions in life is to reduce the level of entropy in the world. And I think your work has done so much to advance that, not in academia, but in the commercial world where these problems are most acute and are most needed. So, Scott, tell us how to reach you.
Sure. I can be reached on Twitter at Scott Havens or via email, scott@sphavens.com. That's SierraPapaHavens.com. I would love to talk with anyone who is interested in applying some of these concepts about distributed asynchronous event-driven systems in their own work, where they may have more traditional architectures and are wondering if they'd be able to see any kind of gains by making it any changes, or how to go about doing so. Or if you have already started on that journey and have experience, either good or bad, with making these changes. Maybe you're having a lot of the same concerns about being able to observe the systems as a whole and how they interact, and your thoughts on that and what's working for you and what's not. I would love to be able to talk with anyone with that experience as well, to collaborate on that.
Thanks so much, Scott.
Thank you, Gene. My pleasure.
The Idealcast is produced by IT Revolution, where our goal is to help technology leaders succeed and their organizations win through books, events, podcasts, and research. This episode is made possible with the support from ServiceNow. Take the risk out of going fast. If you need to eliminate friction between dev and ops, head to servicenow.com/devops to find out more.